Welcome to the keynote speaker session today on the flexible and the interpretable learning for the high-dimensional health data. I'm Zhang, and I will serve as moderator for this session. Before we begin, so I have several reminders. If you have any question for the speaker, you can send it at any time by pressing your Q&A button and enter your question. You also can raise your hand, and I'm not quite sure whether it is a function here, but so you can, if possible, you can unmute and ask your question. Okay, let's start it. So first, for the modern health data, we already see in the yesterday's session, it is massive and high-dimensional and very complex. And the traditional statistical tool actually cannot have a powerful analysis skill to handling this data set. And how could we extract the useful information from the complex, messy, the public health big data set and deliver the actionable and interpretable results is very challenging. Here today, we bring our speaker, Dr. Zhang, from the department, a professor from the Department of Mathematics and at the University of Arizona, as well as the Director of Statistical Graduate Interdisciplinary Program. And Dr. Zhang is currently Editor-in-Chief of ISI Stats and Associate Editor of Journal of Royal Statistical Society Series B and the Journal of American Statistical Association and also Journal of Computational and Graphical Statistics and Statistical Analysis and Data Mining. She is a fellow of IMS and ASA and elective member of International Statistical Institute and IMS Mandarin Lecturer. She is a pioneer actually in the data mining, and her book, Principles and Theory for Data Mining and Machine Learning, was published in 2009. I now pass the floor to Dr. Zhang. Thank you.
Okay, good morning here, for Arizona. Thank you, Jia, for the very nice introduction. This is my first time to attend this big health meeting. And I'm really impressed with the program and the scope of the conference in the program so far. So today I'm going to share with you my work on, non-prometrics for high-dimensional data. And it turns out this actually falls in the scope of how do we make our machine learning algorithm flexible, interpretable, and explainable. Okay, so I just start from my talk here. Sorry, let me see how. So my talk is focused on high-dimensional data. So throughout my talk, I'm going to use dimension, use P to denote for data per dimension, and N to denote for the sample size. So what is high-dimensional data? And it turns out that, the definition is very simple. As long as P is much larger than 3, that's high-dimensional data. So in practice, people actually have, started dealing with the data with increasing dimensionality. Like sometimes P is really large, but still smaller than sample size. Sometimes the P diverges with the sample size. When you collect more samples, dimensionality actually also increases with sample size. And in a very extreme case, the dimensionality P can be much larger than sample size. And so for example, for microarray gene expression data, we know typically the gene, collected at at the level of 22,000. But if you only have hundreds of tissue samples, that is the case, P is much larger than N. So the high dimensionality data actually create a lot of challenges for the traditional statistical methodology, theory, and computation. And so we are trying to extend the traditional works to modern, very powerful tools to extract data, to get a pattern from the messy data. So today I'm going to introduce actually one tool which has been developed, by our group for the past decade, just to show you, why this actually new tool can handle high dimensional data and provide a tool for flexible learning and interpretable learning. So here also I give you some examples, in health sciences or in other, sciences about the broad applications of, these tools called high dimensional data learning. Like, for example, in this brain image science, we have the images of the people's brain and try to identify the interesting, meaningful regions which are related to brain activities. And then we have, for the microarray gene expression data, we collect expressions for multiple genes, try to identify the association between the genes with a certain disease status. We also have network data, and also astronomy data is also a source for large dimension data. And typically for statistical models, our goal is try to establish the relationship between the inputs, which we also call covariates, and y is the response. And we actually, we call this relationship, as a regression function. Here it's just a conditional expectation of y given x. And in supervised learning context, if y is continuous, we know that is regression problems. And if y only takes a discrete value, then that's classification problems. And so here I want in my talk, I'm going to focus on how do we estimate f, how do we make inference f by using our high dimensional data. And so depending on the model assumptions, okay, we make, and we have two big model classes for the transfer models. We know, like, if we assume f has a certain form with unknown regression coefficients, that belongs to Prometric model class. And if we don't make any assumption about the f, and that is a non-Prometric models, okay? And so we know a lot of pros and cons between Prometric models and the non-Prometric models. And typically speaking, Prometric models are simpler, easier to compute, and easier to interpret. And non-Prometric models are more flexible, are more capable of discovering nonlinear patterns, but the computation cost is high, and the theory is actually not easy to study, and so on. So today, I'm going to actually talk about, how do we really extend this Prometric model or non-Prometric models to the learning of high dimensional and complex data. And actually my talk will be focusing on the non-Prometric models. So for whenever we have high dimensional complex data, we want to model the relationship, okay? And what are our desired goals, okay? For the model. So here are some basic principles we try to achieve, okay? We want a model to be flexible, okay, and not only capture linear relationship, also it should be able to capture nonlinear, very complex relations between y and x. Because in many actually complex biological, mechanisms, the linear assumption is just too restrictive, and it cannot really capture the main picture of the relationship between y and x. We also want our models to be interpretable, okay, and we can explain, to our scientists or collaborators, okay, and what is the effect of x on y, x1 on y, x2 on y, and so we actually want to be able to explain our model clearly and to understand the different roles of the covariates on f. And for high dimensional data, typically, because the p is so high, and the model form can be really complex. In reality, we prefer to find a low dimensional structure or approximation for the model. Actually, scientifically, even we have so many genes in cancer studies, and biologists and doctors believe typically there's only a small set of genes which play critical roles in prediction of cancer and so on. So there is a hidden low dimensional structure there we like to recover. And we also want our model to have a certain sparse structure. By sparsity, I mean, and although you collect 22,000 genes, and only a small set of genes are useful. and how can we identify that, some small set of genes? And we know that it's actually the problem of variable selection and model selection and so on. So in literature, okay, in the past, 20 years, more and more tools have been developed to really offer, the new the methods which can achieve all of these, desired goals. For example, like generalized editing models, trees, random forest, deep learning, and so on. Okay, and there are many, many capable and powerful tools, but they all have their pros and cons. Okay, and for example, deep learning random forest, they can deliver very powerful performance, but I mean their theoretical properties are not easy to study, and there's a lot of still opening questions about, for example, consistency, and whether the theoretical guarantee of these works is not clear. And today I'm going to talk about one of our, proposed framework. I call it, Sparse and the Non-Prometric framework. And compared to other works, this framework has some nice, computational properties. I'm going to show actually the optimization is convex. So we can guarantee, the solution exists, and if you use, good algorithms, it's guaranteed to converge to the global solution. And also, more importantly, it has theoretical guarantees. I'm going to show that, under certain, scenarios, our method actually can guarantee to provide, the correct model structure, the correct set of important variables, and also can actually have a model consistency, by which we mean it can actually capture the true underlying function relationship with a certain rate when sample size go to infinity. Okay, so I'm going to spend 2 minutes to review what is a non-prometric regression here. So non-prometric regression typically, we don't make any assumption about the form of f. Okay, in here you can see I have like a red points, which are observations in this small graph. And you see there's two actually curves. One is green, one is blue, and trying to capture the main trend. If you look at here, you can see blue curves seems does a better job than green. And but we want our model, we want our technique method to find this blue pattern automatically, rather than by making assumption that, oh, this f has a quadratic shape or or cubic shape. So in non-prometric method, we just let the data speak for themselves. Okay, so such that it can actually find the more flexible and the nonlinear patterns in the data. And there are many classical non-prometric works which can actually capture these curves, nonlinear curves from the data. So here is just a list of the existing works. You can see from here, most of them actually were developed like back to 30 or 40 years ago. So they are really classical works, like a kernel smoother, sublimes, editing models, and the wavelets. And but then the problem is almost all of these methods, the computation and theory, work for low-dimensional data. Okay, they all typically assume p is really small and fixed, and also p is and the theory also works for fixed p and so on. So the challenge is here is how do I really extend all of them, to non-prometric, to high-dimensional data. So here, just give you a quick review about, if you fit a cubic smoothing splines, okay, and essentially you are minimizing regularization problems, which has two components, and least squares plus some roughness penalty. To understand how spline work, just give you a very simple illustration here. So you can see that we have the black dots, which are the data observations we collect. And then the solid line here is a smoothing spline fit. And we have 9 different fits. And you can see from the first row, all the fits are pretty much linear fits. Okay, we call this kind of a non-prometric fit underestimate. Okay, they don't really capture the main trend of the data. And in last row, you can see our fitted curve actually are getting wiggly, and there are a lot of small bumps here. And although they can capture mean trend, but they actually are overfitting the noise in the data. And the middle row, particularly the sixth plot, the sixth one, and it shows like actually it's actually kind of a perfect, trade-off between the smoothness and also the flexibility of the curve. You can see this actually has produced a very nice smooth curve and capture the mean trend. And so here it turns out the 9 different panels are all given by smoothing splines, but with different tuning parameters. And we need to really figure out what is the best way of tuning these parameters. Okay. And that is for univariate function estimation. If we have a multi-dimension regression, like a P is much larger, and in practice, people actually decompose this function into multiple components. So here we have like a main effects component, two-way interaction components, and all the way up to higher order interactions. In order to estimate these different components, we need to solve a multivariate smoothing spline model. Here is additive models. And so you can see here, we just have a multiple, rich type penalty, like a roughness penalty to the problems. So here is another illustration just to show you, this actually tools is really powerful. Like in this example, we have like a 4-dimensional function, and the black, the black line is the truth, and the red line is the fit given by the smoothing splines. And you can see actually it does really good. But the main difficulty here is if you increase P to be much larger value, okay, this like the computation tool and also the inference is not easy. So here I can show you in this particular case, you can see in the second row, the truths are 0 functions. Okay, the truths, so in here, F3 and X3 and X4, they don't have effects on my F. Okay, the black line is a 0 function. But when we actually fit a regression spline or cubic spline, you can see we don't get exactly 0 function. Okay, we get something approximately close to 0, and something really centered around 0, but they are not 0. In high dimensional data, if we have many noise variables, we will expect to see a lot of this kind of fits. Okay, the fits are really close to 0, but they are not identical to 0. And then we will wonder, how actually are they really significantly different from 0 or not? Okay, so how do we know, these variables are really important or not? Okay, so that's actually, directly is a question I'm going to actually try to answer by using a new framework. Okay, so basically we want to answer all of these questions. So does F have an additive structure or higher order interactions? So which variables are important? Is F linear or nonlinear X1, and so on. Okay, so if you put all of these questions, I here give these questions in very abstract way, but if you put these questions in a concrete example for health science applications, this actually is one of the my collaboration project, with researchers in pharmacy. In this project, we like to predict the opioid overdose based on patients' information, which include social demographic variables, health status, and utilization patterns, and the provider information. So we want to actually particularly answer the following questions. So for example, does the age, or gender have a linear effect? Or does age have a nonlinear effect? We want to know which covariates are useful to predict opioid overdose. Is there an interaction between age and gender, and how to identify high risk group for overdose. Okay, and so they are typically in the typical questions we want to answer, from statistical perspective. But here, imagine the dimension of P can be high. So it's actually this question is actually to answer these questions, it needs like a more powerful tools. So the work I'm going to present here actually will follow two principles. One is called the smoothness principle. As you can imagine, my function component should be smooth function. Okay, it should also at the same time follow sparsity principle. Okay, so basically, I hope majority of function component I estimate they are truly zero functions. Okay, and I hope my estimator can actually produce exactly zero functions, so I can get rid of some variables. And so my framework will actually be introduced in the context of this reproducing kernel here of the space. I know this actually is maybe beyond the scope of maybe a lot of people in audience. So you don't need to worry about these slides. I just want to show you there is a very rigorous mathematical framework behind the talk I'm going to the method I'm going to introduce next. So roughly speaking, all the functions we are going to estimate, we will assume they live in a very nice function space in a function class. Okay, and that function class actually is a Hilbert space, and all the functions we can define their norms, and also we can define the scalar product of the two functions. And so on. Okay, so basically this is related to reproducing kernel Hilbert space theory. And the reason we adopt this framework is that it provides a very rigorous framework for function estimation. Okay, for now you can just ignore this method, ignore this RKHS. Okay, so I'm going to define an operator called the smoothing and selection operator. Okay. And this operator is really, really general, okay? And it's actually proposed a very, broad framework, regularization framework. And I'm going to show that, this principle actually can be applied to many, many models that we encounter and use, in our research, okay? So for example, I'm going to talk about the applications of this operator in 4 different models, okay? The first one is just generalized additive models, and the second one is partially linear models, okay? Then we also can have the application of this operator into the functional additive models and also non-prometric interaction models, okay? Just show you, using one simple operator, it turns out in different contexts, we actually can further extend this operator to study and answer the questions in our hand. Okay, so what this operator looks like, okay, this operator just looks like a regularization, framework, which has 2 components. The first component is just we want to minimize these residuals of my fit for the data. Here, yi are my responses and f is my predicted function value. And the second term is something that's a magic term, and this is a trick we are going to use to encourage both smoothing and selection. So if you apply this operator to your framework, we are going to show that in the end of the day, this f, you estimate f. Okay, we estimate f in some function class capital F here, which is a reproducing kernel Hilbert space. But we're going to show that this f will be smooth and also has a sparsity property. Okay, and so this actually is just a theory, just to tell you, we can prove when sample size go to infinity, and the minimizer of this, Yeah, the minimizer of this function exists, and also in order to find it, we only need to solve convex problems. Okay, And so we have some theoretical proof results to show that solution exists. It also has a finite representer theorem. And this theorem actually is really, really, important to show us, we actually only need to deal with a finite dimensional problems. And so actually, it's actually kind of changed the problem from infinite dimensional optimization to a tractable finite dimensional case. So I'm going to skip the convergence result just to believe me, we can show that the f hat, it can approach to the truth. And also more importantly, if you tune the parameter properly, then we can guarantee that we can capture the important component. And for the non-important component, actually we can show that their estimate will be identical to 0. In order to show the performance of this operator, I'm going to show you an example like which we have 60 dimensions of the data and the sample size is 500. Okay, and the underlying truth, only depends on 12 important variables out of 60, and we want to check, whether my causal principle actually can capture this 12 out of 60. And this actually is typically not easy problem to estimate because you only have 500 samples while trying to estimate a function in 60-dimensional space. Okay, so here is a table just to show you one case of our causal principle. And the table shows you the number of important predictors captured by this principle out of, remember the truth is 12. And the second row shows you here, like in average, the causal with this 5-fold cross-validation can capture 12 important predictors. And the model is really sparse. So all the remaining, predictor functions will just be estimated as 0. Okay. The last row is a model we compared. It's also another very popular approach called MARTH. And you can see in average, MARTH actually identifies 30 some variables out of 60 variables. And we also did a more extensive work to make our causal procedure as an oracle procedure. And if you are familiar with the linear model selection, what we care in most is that we want to select the important variables at the same time, and we don't want to sacrifice the prediction efficiency in the model. It turns out the principle I showed you earlier, causal itself is not an oracle procedure. And so we decided to make it, oracle by extending the causal framework to a weighted causal framework. So this is another example. There's another paper we did after the original causal paper. We show that when if you introduce a weight in front of the reproducing kernel norm, actually you can achieve the oracle properties. And so here's theory about oracle properties. And this picture show you how you really implement causal in practice. And we have a package for causal, and you can draw the solution path, okay, for causal and adaptive causal. Here the x-axis is a tuning parameter. Y-axis, it tells you, which component are in the model. And so here we plot the L2 norm of each component. And as you can see, if you choose n equal to 4, and some component will be in the model because they have a non-zero norm, and the other component will have a 0 norm because they will be estimated as identical, as exactly 0 function. And okay, so that is really just a very general additive model. Now I'm going to show you 3 more model classes where actually you need to twist the causal a little bit, okay, modify the causal, and then it turns out it can solve other very important problems. So this actually is the model called the partially linear models, and I think it's very popular in use in practice. You have many covariates. And you always wonder, okay, which covariates have linear effects, which covariates have a nonlinear effects, okay? And it turns out that that's actually not easy problems. And at least before our paper, we found there's no really method with theoretical guarantee to tell us, okay, if you apply my procedure, I can guarantee to identify linear effects and nonlinear effects. I can separate them into different classes. Okay. So here, you know, the main question is we want to know which covariates have linear effects, which have nonlinear effect, which have zero effect, basically no effects. So that's a problem of a structure selection problems. Okay. At the same time, we want to estimate non-zero betas and FKs and to make inference. So that is estimation problems. And so how do we solve these problems? And the trick to solve this problem is we go back to the reproducing kernel Hilbert space, and we do another more detailed level of decomposition for the function space. We decompose the function space into linear space and the nonlinear space. And correspondingly, we also decompose each function into linear component and nonlinear component. Okay. And after we do this decomposition, we can actually extend our causal operator to another operator. We call it the land operator. So you can see land operator actually has two terms in the regularization form. The first term is for like to penalize the linear terms. The second term is to penalize nonlinear terms. And it turns out, you know, if you solve these problems, it's also convex problems. We have two tuning parameters, okay? And if you solve this problem, you can guarantee a lot of, you know, desired properties. We can show that solution is guaranteed to exist and lies in a finite dimension space, and the solution, the function estimator can achieve the optimal non-prometric rate. And more importantly, under certain conditions, if we can choose the weight and the tuning parameter properly, we can actually show that the estimator, you know, can identify the correct structure asymptotically. In other words, when your sample size go to infinity, and the linear effects will be estimated as linear effects, and the nonlinear will be actually identified as nonlinear effects, and the non-important effect will be thrown away from the model. Okay, and so here is just one example I want to show you. So in this case, you know, we have like 6-dimension variables, and you can see the x1 and x5 here. They have linear terms, and x2, x3, and x4 they have a very nonlinear, you know, effects. Okay, they have like have nonlinear patterns in the regression function, and x6 has no effect in my model. Okay, so again here the black is the truth and the red color as a fitted line. Okay, you can see this is the one, you know, fit given by the land estimator. Actually, it can actually capture this linear pattern, nonlinear pattern, and also identify exactly zeros for those covariates which have no effects. Okay, so we call this very, you know, it's called kind of structure selection problems, and also the land actually can give us guarantee about the structure selection consistency. So the next one very exciting framework. We found all actually causal principle can be applied to nonlinear and to the partial linear models. And then later on, when we have in our collaboration, you know, with imaging science and the brain image scientists, they typically collect the brain images. So in their case, you know, the data are not the standard vector, multi-dimensional vector data. Their data is a functional data, okay? And so functional data essentially just tell us, you know, we observe the curves for each X covariate, okay? And they wonder, okay, how do I modify the relationship between the curve, you know, inputs with my response, okay? So this actually is where, you know, the functional PCA, functional principal component plays a critical role. And so the fundamental framework here is, first of all, we are going to re-express, our estimate and our observed function curves using the Kahoot-Loewe expansion. So basically, just represent each curves by using a number of basis functions. The basis function typically are generated by using the eigenfunctions of the covariance process. Okay, so we actually can extract a big number of coefficient here, Xi, we call them function component, a PCA score, FPC score. And then when we model the relationship between y and x, we just model the relationship between y and the function PCA score. Okay, and when you do this Kahoot-Loewe expansion, typically this expansion has infinity components, because when you do the eigenfunction decomposition, actually this covariance process has an infinite dimension principal components. And what people do in practice, in order to really, we have only limited sample. Okay, how do I estimate this BJ infinite number of parameters? We cannot really, it's not really practical. So in practice, people just truncate this expansion by just retaining a top number, by retaining the top of principal components. Okay, so that's what people do. I call it a truncation procedure. Okay, you just truncate the series by keeping this principal component with the highest variance, and then you just do the function estimation by using the high order principal components. But is that really a good idea? And that has been done in practice. But people, in recent studies and applications, people find out in some situations, and this function principal components, which have actually small, principal component, small variance, they actually can contribute more significantly than the leading principal components. So here, leading principal components have a higher variance, and the high order principal component have a very small variance. Okay, so this actually suggests maybe it's not a good idea just to truncate this series, and otherwise you should actually select which component in this series actually is more important, rather than just by blindly assume, okay, only top principal components are important to predict y. Okay, and this actually is related to the work called supervised PCA or unsupervised PCA. Because when you do a standard PCA, you really don't look at the relationship between y and x. You only look at the structure of x. And so here we want to actually just think about how do we really take into account the relationship between y and x and do principal components there. So this actually is another extension of our work, where we actually can show that the principal component actually, the castle actually can be applied to these functional additive models by selecting important principal component and improve the estimation. Okay, so here is just I think I'm out of time. I'm just going to show you one actually study where we actually in this study we actually look at the role of all the top 20 function principal components. If you actually you notice here, and for some actually, if you do the traditional work, you will maybe just keep top 2 or top 3 leading components. But here we actually can able to show that some actually top principal components, they have no effects. So here, for example, F9 has no effects. And some some higher order principal components here, F16, F6, 17, they actually have a non-zero effect there. Okay, so here I just show you, using this causal principle, we are able to actually identify really informative function component rather than just keeping the high order one. Okay. So and also we have extended this work to do interaction selection, and because of the covariates, they do talk to each other, and they have this synergy effects among them. So that's really ongoing work. We have done some interaction screening for ultra high dimensional data for the Prometric setup and in recent years. And now we are actually trying to, we are actually doing the work to combine the causal with the interaction effects. Okay, so I think I'm done here, and this is my last summary slides. So hopefully, the take-home message is, this new theoretically developed principle called the smoothing and selection operator in a mathematical framework called reproducing kernel Hilbert space. I show that actually this operator actually can be applied and it can be extended to solve many real problems for high-dimensional data, structure selection, and function estimation. Okay, I think I'm done here. I'm sorry for going over time, just ready for questions.
So thank you very much for the nice talk on the behind the mathematical work, behind all the software we have. And so I do have a very simple question about because the causal already being available in R, and so lots of the audience actually will use the existing package in R to do some machine learning technique. So could you give some recommendation or some remind about when they try to compare different packages they try to choose, and when will be the good time they will choose causal and you develop instead of other package?
Oh, you're saying comparison again between causal with other like the random forest and
right.
and
yeah.
models.
Yes.
Yeah. Typically, the answer to this comparison questions, I always say there's no method actually which works for all the different applications. And so in reality, I always suggest practitioners to combine to implement the different softwares and to look at the result to see whether they are consistent or not. And so causal is particularly really good, and chatbot here is really good for the main effect selection. And for now, for the interaction selection, we can actually handle like I showed you the number of variables, like 60, hundreds, and so on. If you really have a really high dimensional data, like thousands or even tens of thousands, and in order to implement the causal, we will always suggest to do some pre-selection or screening feature, screening pre-selection, before you actually can implement the causal. So that's actually, although it's a complexity, but the computational cost is still not really that low. It's maybe compared to if you really need something really fast and a quick method, maybe random forest is actually a good way to start. But another thing is if you do like random forest and deep learning, you don't really get a closed form, very nice mathematically elegant form. It's really black box algorithm, and it's really hard to identify. For random forest you can rank the variables, and for the deep learning, it's like it's really there's no really good theory to guarantee that you can get the correct model structure. So if you really the theoretical guarantee is really important, and if you really want to have some confidence about the results, and the causal will be a way to go because it has like theoretical, nice theoretical properties and justifications.
So thank you very much for this explanation, and also give all the guidance, some little bit idea about how to choose the random forest and why for the mathematician and statistician, we're still working very hard in this high dimensional data analysis framework in order to provide the best method that can be used for the future. So, and we will end up the session today, and you still can put your question in the Q&A session in the VOVA if you have, and Helen can continue to answer any question if you have. And after this session, we'll have a coffee break. And then afternoon, we still have several excellent workshops ongoing. One is the SAS Maya workshop, and we all have the computational modeling workshop, and the other one is the R25 training program workshop. So see you this afternoon. Thank you.